This is my lab 4 on oscillations. So the introduction, so the purpose of this lab is basically to predict the motion of a system with a spring and a mass, and our system is the mass, earth, and the spring, and the surroundings will be nothing, basically. So we're going to have delta E equals 0 instead of work, because nothing's going to be doing work because nothing's in the surroundings. So our fundamental principles are Newton's second law, which is F net is going to be delta P over delta T, and then we're also going to have energy principle, which is delta E equals Q plus W. Here, the temperature is going to be the same, and then work is going to be 0 because there's nothing in the surroundings doing work on the system. So our other equations are going to be kinetic energy, gravitational potential energy, spring potential energy, total energy, force due to gravity, and then velocity and position update formulas, and then the period, which is T equals 2 pi R over T. So our experimental model, this is basically showing with the initial conditions, it's going to basically look like this. So there's like an object like that right here, and then it's like just moving like in that direction kind of, and that's like from the spring kind of. And our initial conditions, so our time is going to be 0, velocity initial is going to be 0, position initial is going to be negative 0.112, negative 0.632, 0 meters, and then gravity due to Earth is going to be 9.8. And then the mass of the block right here is 0.402 kilograms. Spring constant is 6.83 that we calculated. And then the relaxed spring length is 0.123 meters that we set. And then the computational model, so again, L is going to be the position of the ball minus the spring, right? And then L hat for the direction. And then you have your S, which is your L minus L naught. And then you're going to have the kinetic energy formula. We're gonna have the gravitational potential energy formula right here, which is basically mg delta H, and then we're gonna have the spring potential energy formula, and then total energy, adding all three together. And then we have F grav total, like basically from 0, negative mg 0, right? And then F spring, F net, which is both of them combined. And then we're going to have the position update, so ball velocity equals ball velocity initial plus F net over ball mass times delta T, and then the position update formula, and then again the L hat updating, so it's updating L, sorry, not L hat, it's going to update L, or the magnitude of L, so L minus L naught, the spring compression or extension. And then that's basically going to happen, and then we're going to again calculate these energies again. So now our results, right? So the first results is the experimental system and the computational model are relatively the same because we have the wave like pattern, the sinusoidal kind of wave shape pattern, and that's what we're supposed to have. And then the second results, they show that the total energy is summed to 0 following the energy principle. And this is in the system because the spring, the gravity, and the kinetic energies cancel out, or they balance out, right? So like one goes up, one goes down, like that, they balance out, and then the total energy is 0. So discussion question. So for the model, does it satisfy the energy principle? And as shown in the results 2 slide right here, it does satisfy the energy principle because all the energies, the kinetic energy, the gravitational potential energy, and the spring potential energy, they all add up to 0. So basically change energy 0, total energy 0. And at any given point. And then now to discuss, and the second question is to discuss the tracker data and experiments in the X versus time versus the Y versus time. So from the X, our period was 1.62 seconds, and the Y, our period was 1.55 seconds. This is through the math of T equals 2 pi R over T, like period equals 2 pi R over time. And then we use the period to calculate K, right, the spring constant for the spring, and therefore this discrepancy in the time, right, the two discrepancies, 1.62 versus 1.55, affect our value of K, and basically they just cause the error in our results. And the human error, so in the experiment, while letting go of the system, maybe the human, the experimenter basically pushed the thing a little bit, the block a little bit, like we might have accidentally done that. Or experimental error, so not accounting for certain confounding variables, or the error led to here, right, in the discrepancy in the period. That's also our experimental error, and then there's also calculation code errors that could have possibly been there. So this is my lab for oscillations. Thank you.